real life, we often hang up a sign out in front of a tavern to try to increase business, right? And this is a classic case of what we call two-dimensional equilibrium. Remember what's in the word equilibrium? The word equal. The forces have to balance out in two dimensions in this case, in the x direction and in the y direction, so that there is no acceleration there. So let's say we're going to hang a big sign up here made out of wood for our tavern. Oh, root beer. There we go. Bad Mr. Lau. There we go. Now we're school appropriate. Thank you. So in real life, how do you hang up a sign? Usually you need some kind of chain that holds it up, and that creates what we call tension, a force in a chain or a string or in your muscles. And notice what's tricky. It's pulling up and at a what? Angle, right? Let's make this like 52 degrees. We'll pick a random angle, something like that, 52 degrees. And then that annoying force that opposes us all the time. Yeah, the pull of gravity, which is always which way? And I'm going to pick this point because that's where everything attaches to on the sign. In real life, we would think of the weight on the sign at the center of gravity, which is the center of the sign. But we're just going to say it's acting right on that corner. And the pull of gravity, if you recall, is equal to mass times acceleration due to gravity. Why don't we make it a nice, easy number? I'm going to make the mass 100 kilograms. Nice and easy. 100 kilos. And gravity is negative 9.8 meters per second squared. So if you do the math, how many newtons is that? This is nice and easy, right? It's just going to be what? Negative 980 newtons. Nice even number. So in other words, this sign is roughly 220 pounds. 1 kilogram is about 2.2 pounds roughly. So it's a nice 200-pound fine mahogany wooden sign for our tavern here. There we go, fresh root beer. Yay. There's one last force we need to picture. One last force. There's one last force we need to account for, and what's that? How come the sign doesn't fall? Because the string does what? It does two things. It pulls which way? It pulls up and sideways, right? There's tension in the y direction, and tension in the x. So why doesn't the sign, it doesn't fall because there's tension in the y, but why doesn't it get pulled in towards the building? What's holding it out? There's a big what? There's like a crossbar, right? So we'll just say the crossbar is pushing which way? Sideways, right? So let's just call it the force of the bar, whatever, with a B. Doesn't matter. It's kind of a way to picture it there. And you know what? Since we already drew this little vector triangle, let's go ahead and break it down. How do we express the x component, the horizontal component of force, in terms of the hypotenuse t, if this is my angle in there? Is this the adjacent side to the angle or the opposite side? Adjacent, right? So how do we find adjacent to hypotenuse? Which trig function? Tx is simply equal to, t times the cosine of 52 degrees. And how about this? How about the vertical component? That'll be what? T times the sine of 52 degrees. And you're like, oh my gosh, do bar owners really do this? Probably not. But they might hire a bar sign physicist to help you figure it out, right? Probably not. They would just buy a really fat chain. But in this case, we're going to try to figure out what's the minimum force necessary to hold up that sign. Now what? This was step one, by the way. It was actually pretty complex. And in step one, here's what's different when we do a force problem. You need to draw a special picture called the FBD. You guys remember what the FBD stands for? The free body diagram, which is simply a picture of all the forces acting on a body. In this case, the bar sign. Next, we're ready for step two, which is to list all the what? List all the information. Here's a little trick, kind of like what we did for projectiles. Let's list the forces in how many directions? In two directions. I'm going to do it up here so we get a little bit more room. In the x direction and also in the what? In the y direction. In the x direction, we only have tx, which is t times the cosine of 52 degrees. So we kind of don't really need to write that again. And then force of the bar, which we don't know. But in fact, you can already figure it out using common sense. They're just what? They're just equal and opposite to each other, right? According to Newton's third law. If the chain pulls on the sign in the x direction to the right, that's negative, right? The bar is going to push out to the left in the positive direction. Actually, I flipped it around, other way around. We usually call left negative, right positive. So in the x direction, we really can't solve anything because we don't have enough information. So guess which direction we do look? In the vertical direction. In the vertical direction, what's holding the sign up? T what? Ty. which is equal to T times the sine of 52 degrees. And the tension in the y direction is opposing the weight of the sine, right? Which is negative 980 newtons. So now we pretty much almost solved the problem. You're like, really? Yeah, really. The hardest part of a problem is knowing what the problem is and breaking down the information. So what is this problem? We're trying to figure out how much tension, right, can hold up this 100 kilogram sine. So step 3 is we write out the equation that relates our knowns to unknowns. And in this unit, it's a big idea equation. And the big idea is Newton's second law, which simply states that the net force on an object is equal to its mass times acceleration. It's the second most famous equation in all of physics after E equals mc squared. And you're like, wow, that looks so simple. It is a very simple and elegant equation, but it's very powerful. What you have to realize is it's a net force. It's the sum of all the forces acting in any direction, in x, y, or z, 3 dimensions. You can even go 4-dimensional if you keep track of that. I don't know what that means, though, like you travel through time and push on something, whatever, right? And then acceleration is also a vector. It's a rate of change of a rate of change in meters per second squared for metric units in the same direction as a net force. Very powerful. Let's make our lives easy. We're going to look at this in which direction? Which one's useful? In the y direction. So in math notation, remember, guys, sigma? Sigma just means what? The sum of, right? The forces in the y direction is equal to mass times acceleration in the y direction, which in this case is 0 because the sign is in static equilibrium. The forces are equaled out. The sign is not moving around, right? You're not trying to kill people as they come into the store, right? So in the y direction, what are the two forces? It's easy. We just have what? We have tension in the what? Y direction, and it's opposing weight, the pull of gravity. So in this case, Ty, which is T times the sine of 52 degrees, plus weight, which is negative 980, is equal to 0. Or in other words, the tension in the string supports the sine against the pull of gravity. So if I add 980 to both sides and then just divide by what? By 52 degrees. So now let's go and get out our calculators. You get out yours, I'll get out mine. And make sure that you're not in radians, but in what? In degrees. And then make sure when you go back to math class, switch back to radians so you're not messed up. So we're simply going to take 980 newtons and we divide it by the sine of 52 degrees. And use common sense. Is it going to be more than 980 or less than 980? Just think about it. It should be what? It's going to be more than 980, right? Because the tension in the string has to support the sine in the y direction and pull it sideways. So in this case, we get T to be 1,243. Good enough. I guess we'll keep one decimal place, 0.6 newtons. So 1243.6 newtons is the total tension in my string here, big T.